All right, grade 11 chemistry. Yesterday we talked about the mole concept and just how big a mole is and just how tiny atoms are, basically. Today we're going to apply that to chemical reactions. First, we're going to do a little bit of history, though. So here's what we're going to talk about today. We're going to do a little bit of history. Then we're going to have an analogy for the mole ratio and what it is. And we'll do some example problems that involve the mole ratio. So a lot of this video is just going to be example problems. Starting with some history, please note I won't ask about history, but the concepts in that history are going to be fundamental to our course. So if you want to know where the stoichiometry, the actual mathy bit of chemistry starts, we can blame Antoine Lavoisier, who was a French guy. 1789 he published this book that laid down a lot of groundwork for a lot of chemistry. Groundwork we still use today. So, for example, well, here's a quote from him: "Nothing is lost, nothing is created, everything is transformed." So, he was one of the first people to really nail down the law of conservation of mass. He made a lot of apparatuses that let him calculate very precisely how much mass was gained and lost in chemical reactions. He started the entire idea of binomial nomenclature, so like sodium chloride and zinc sulfate and stuff like that. That was him. He named hydrogen and oxygen. He kind of conclusively proved that water was hydrogen and oxygen, was two separate elements instead of one. That was working off of previous research from other people like Henry Cavendish. He also did the proof that oxygen causes combustion. So he's the guy we were talking about during the lab that studied combustion and kind of did away with the phlogiston theory of combustion. He also, in that same book, wrote one of the first modern lists of elements. So he was like, okay, hydrogen's an element, oxygen's an element, carbon's an element. He got it kind of wrong. Like he said sulfate was an element because I guess he couldn't break it up into sulfur and oxygen. And he said sulfur was an element too. So like it was kind of interesting. But anyway, he also identified that like sulfuric acid was sulfate with hydrogen attached to it, so he had kind of a conception of acids and bases at the same time. Really cool guy. And sadly, he was executed just after the French Revolution at age 50 because he was part of like a tax thing for tobacco, and they didn't like that he made tobacco more expensive and stuff like that. There's a whole story there. But yeah, he's the guy we blame. He started this whole stoichiometry thing. And working off of his research, we have Proust, who was also French. A bit later in the 1790s, he figured out the law of definite proportions. So he did a lot of measurement using the same kind of techniques that Lavoisier developed. And he noticed that the mass ratios were always the same no matter the source. So like CO2, which they called fixed air back then, he noticed that fixed air, no matter where he got it from and how much of it he always got 12 grams of carbon and 32 grams of oxygen, or if he got 24 grams of carbon, he'd get 64 grams of oxygen, or 36, he'd get 96 grams of oxygen. So it was always like this interesting ratio of 12 to 32, or I guess 6 to 16 in the masses of carbon and oxygen that were coming off of this CO2. So that was kind of the first hint of chemical formulas, of being able to bring it down to chemical formulas. And of course, the big guy for chemical formulas was Dalton. So I'll move myself down here. Dalton, who came up with, it wasn't the law of definite proportions. Definite was just a single element. Dalton came up with the law of multiple proportions, so multiple chemicals. So he took something like nitrogen monoxide that he worked out you could make from nitrogen and oxygen, and nitrogen dioxide that he also worked out you could make from nitrogen and oxygen. And he noticed that, using Proust's idea of definite proportions, he noticed that the proportion was like this all the time, and this proportion was like this all the time. And he noticed that if you keep this the same, 14, 14, that this one always had like a round number proportion. So he brought it down like 1 to 1.143. This one was 1 to 2.286, twice as much. And so he noticed that the proportions were always the same. And he was particularly interested in oxides. So whole number ratios was his thing. Right? Took the law of different proportions and expanded it to this, the law of multiple proportions. And so this created the underpinning of his atomic theory. And as we know now, Dalton's atomic theory prevailed in the scientific thinking of the time. This whole sequence from Lavoisier through to Dalton and a bit after that is something called the chemical revolution. So it's when we actually figured out, well, Europeans, I guess, actually figured out how to name chemicals, how to think about chemicals, and nailed down this chemical formula business. And a bunch of people contributed, starting in about the mid-1700s and finishing, in the mid-1800s. There was this 100-year period where chemistry just went nuts. A lot of it had to do with the invention of electricity, actually, because electricity made chemistry a lot easier. So that's kind of cool. So that's all of our history there. We're going to talk about the mole ratio now, right? That's our next thing, an analogy for the mole ratio. So I'm going to pause and get that set up. All right, so let's do an analogy for the mole ratio. Let's pretend I'm making a sandwich, right? And the sandwich is going to be just ham and cheese, So what does it take to make a sandwich? Well, it takes, terribly drawn, but here's 2 slices of bread. They kind of look like mushrooms. Make them bigger. 2 slices of bread. 2 slices of bread. 1 slice of, we'll say, ham. All right, and 1 slice of cheese. Okay, so bread, ham, cheese. Maybe that could be the cheese, whatever. So that would be 2 bread plus 1 cheese plus 1 ham is going to give me my sandwich. Right? Bread, 2, cheese, ham. Okay, that's my sandwich. Bread, 2, cheese, ham. The common name for this is a sandwich, but it's bread, 2, cheese, ham. This is the ratio for a sandwich. So the ratio is always 2 bread to 1 cheese, or 2 bread to 1 ham, or 2 bread to 1 sandwich. Right? The sandwich, if we draw it, it'll look like this. There's the cheese. There's the ham. There's the bread. There's the ham. There's the cheese. And there's another piece of bread on there. All right, so there's a ratio, 2 to 1 to 1 to 1 sandwich. 1 sandwich. We can ask ourselves some questions, right? A loaf of bread. Let's say I have 12 slices in a loaf of bread. Actually, it's typical loaf of bread, 16 slices. 16 slices of bread. How many sandwiches could I make? Right? How many sandwiches? How many sandwiches? And the obvious answer is 8. Right? We can make 8. Make 8 sandwiches because each sandwich has 2 slices of bread, and that's how we that's how we could figure it out. We just divide by 2, and it's kind of obvious. If I had instead, 13 pieces of ham, I could, if I had enough of the rest of this stuff, make 13 sandwiches. Right? I would need, for my 13 pieces of ham, I would need at least 13 pieces of cheese, and I would need at least, how many? 26. 26 pieces of bread. 26 pieces of bread. Alright, so that's the mole ratio. The mole ratio, very simply, is just numbers. But instead of a number like an actual, easy number to count, we've got a number of moles. So a number of the huge pack of atoms that we use So that's the mole ratio. The mole ratio is a number. That means you could have a number ratio of, there'd be 2 billion bread, 1 billion cheese, 1 billion ham. You make 1 billion sandwiches, which means you could have like 0.3 billion pieces of bread, which means you'd need half of that, 0.15 billion pieces of cheese. So the mole ratio can be fractional as well because of the massive number of chemicals in a mole. So let's jump back to the mole ratio and we'll talk about it, right? So here's the mole ratio. Here's another example. S'mores, 2 crackers, 1 marshmallow, 3 chocolate squares gives you 1 s'more. So 2, 1, 3, and you get the same kind of concept, right? The mole ratio between crackers and marshmallows is 2 crackers to 1 marshmallow, and 2 crackers to 1 marshmallow will also be 2 moles of cracker to 1 mole of marshmallow. Just like 2 billion pieces of bread can make 1 billion sandwiches if you have enough of the rest of the stuff. So that's the analogy for the mole ratio. Here's like a chemical treatment of it. Here's the synthesis reaction for sodium chloride. You need 2 sodiums and 1 chlorine because the chlorine molecule is a single thing that has 2 atoms in it. And you make 2 sodium chlorides. So if you want to make 2 moles of NaCl, you need 2 moles of sodium. If you want to make 1 mole of NaCl, it would take 1 mole of sodium, and so on and so forth. We have a ratio. And the ratio, right, the ratio can be expressed as a rate. Right, rate kind of folds into ratio. When we have this NaCl, it's 2Na plus Cl2, making NaCl, 2 of those, 2 NaCl. If I had 0.3 moles of sodium, I have 0.3 moles of sodium, I could make, I think it's pretty obvious, 0.3 moles of NaCl, because it's a 2 to 2, which is basically a 1 to 1. But if I had 0.3 moles of chlorine, right, 0.3 moles of chlorine, and as much sodium as I wanted, it's not 0.3 anymore because it's 1 of these to 2 of these. Every 1 chlorine gets me 2 sodium chlorides. And so I would be able to make twice that, 0.6 moles of NaCl. And so on and so forth. Remember that mole is a big number, like billion. It can help you understand it. I have 0.3 billion sodiums. I can make 0.3 billion sodium chlorides. I have 0.3 billion chlorines, and 1 of these makes 2 of these, so I can make twice that, 0.6 billion sodium chlorides. And so we can run things through a ratio. What if I wanted to make 1 mole of NaCl, right? What if I wanted to make 1 mole of NaCl? What would I need? What would I need to make 1 billion NaCls? Well, I mean, obviously you'd need 1 mole of sodium because it's a kind of a 2 to 2 ratio, a 1 to 1 ratio. How much chlorine? How many moles of chlorine do I need? Right? How many moles of chlorine do I need? Well, I think it's obvious because it's a 1 to 2. I need half as much chlorine as the amount of sodium I'm going to be making. Right? Kind of like when you're making a sandwich, you only need half as much, ham as the amount of bread that you have. If I have 12 slices of bread, I only need 6 slices of ham. So I need half a mole, which is fine because remember that mole is something like billion or dozen. You can have half a mole. You can have tiny fractions of a mole because a mole is such a stupendously large number. So that's an analogy for the mole ratio. Next up, we're just going to do a bunch of practice problems. So here's a practice problem, and what we're going to do, I'm going to talk about conversion factors and how conversion factors can help us think through a problem like this. We have this reaction, iron and oxygen combining to make iron oxide, and we are looking at this question: how many moles of Fe2O3 of iron oxide of the product can we form if we have 6.3 moles of O2? And the second question I'm going to ask is a different question with different answers. we do it again and we make 12.1 moles of Fe2O3. Well, the question was how many moles of iron were in the reaction, in the original reaction. So I've written this down on the whiteboard, and we're going to solve it using the conversion factor method. And here's how it's going to work. We are going to create some ratios. Right? Here is O2. We want to go to Fe2O3. And this is just the question that was on the thing. I have 6.3 moles of O2. How much Fe2O3 can I make? Well, when we look here, O2, it's 3 of these for every 2 of these, which is a fraction. So what we're going to do is we're going to do that conversion factor thing. If you're confused about the conversion factor method, please watch the previous video where I explain it. And the conversion factor method relies on being able to cancel out our units. So this one is moles of O2, so we're going to want O2 on the bottom. O2 on the bottom. And we're converting to Fe2O3. We want to have Fe2O3 be the remaining unit, Fe2O3 on top. Then the numbers for those, the ratio for those, the mole ratio, comes from our equation, our balanced equation. This is the reason for balancing equations. We can figure out how many moles of each thing we're going to make. So if I have O2 is on the bottom, I'm going to put that 3 there, which is up here from the equation. And the Fe2O3 gets its 2. And so that gives me exactly what I need to do mathematically to answer my question. Right? I'm just going to put it through my calculator. 6.3 times 2 divide by 3. The O2 is going to cancel. I'll just show that here. The O2 is going to cancel. We're going to be left with moles of Fe2O3 because, math. So 6.3 times 2 divide by 3. Let's try it out. 6.3 times 2 divide by 3. 6.3 times 2 divide by 3. 4.2. 4.2. So 4.2, but the moles is still there too, right? Remember, it's like 4.2 billion. It's 4.2 moles. 4.2 moles of Fe2O3, and that's our answer. Right? Easy peasy. We don't need to do our heads in thinking, do I multiply, do I divide? The conversion factor method helps us work it out, and the ratio comes from the balanced equation. Everything in chemistry kind of feeds into itself. We build up as we go along, a lot like a math class. Now the second one, a similar question. All right, the second one's a similar question, but here I have a certain amount of Fe2O3, and I want to figure out how much Fe, right, how much solid iron can I make. But we're going to do the same thing. It's going to be a conversion factor. We're going to multiply by something. And in this case, we want to cancel out our starter, right, our Fe2O3. So the Fe2O3 is actually going to be on the bottom now, because that's going to cancel top and bottom. And on the top is going to be what we're interested in, because that's going to be left behind once we do our calculation. And here it's the Fe, the solid iron. So the iron, right? We write that out. Then we get our mole ratio from the equation. In this case, 4 Fe, so it's 4 up here, and 2 Fe2O3, 2 Fe2O3. So we're going to be here multiplying by 4 and dividing by 2. If you're clever, you'll notice that you can just multiply by 2, and that's true here because we get 4 of these for every 2 of these we make, so it's just going to be double. But this is a way to codify it, so we can just put it through as is. We can go times 4 and then divide by 2, end up with 24.2. We're going to end up with 24.2. And it's not just 24.2, it's 24.2 moles of iron. Remember, it's like 24.2 billion. If you just write 24.2 without the moles, it's like saying that Jeff Bezos has $122 instead of $122 billion. So 24.2 moles of iron is created there. So there's a practice problem. We'll try one with a different reaction. So I'll pull up one with a different reaction. Just give me a sec. I'm going to pause. So here's a different reaction. Nitrogen plus hydrogen gives us ammonia. This is the Haber-Bosch process. And we have some questions, right? Let's say I have 1 mole of nitrogen. How much ammonia could I make? 1 mole of nitrogen, how much ammonia can I make? I mean, it's 1 of these makes 2 of these. So if I have 1 billion of these, I'll make 2 billion of these. If I have a mole of these, I'm going to make 2 moles of these. We know the answer is going to be 2 just intuitively, but let's go through the whole process here. We're going to multiply it by our conversion factor. We're going to make a conversion factor here. The conversion factor is going to have nitrogen on the bottom, and there's 1 of those in our mole ratio. The top is NH3, which is, there's 2 of those in our mole ratio, 2 NH3. The nitrogen is going to cancel out, leaving the ammonia, and so it's going to be 1 times 2, which is 2. Right, 2 moles of NH3. This one, we've made 10 moles of NH3. How many moles of nitrogen were used up in the reaction? We're going to have to make another mole ratio. But in this case, in our conversion factor, NH3 has to be on the bottom because we want to cancel it, just like we canceled this N2 here, right? We canceled that. We want to make that on the bottom. And in our reaction, the NH3 has a 2 as the coefficient. And we want to make N2, so that's what we're looking at, N2. And N2 in our reaction has a coefficient of 1. And so in this case, we are dividing the 10 by 2. We're multiplying it by 1/2. We're dividing it by 2, which means 5 moles of N2. Hopefully you guys are getting it so far. Let's do something a little bit more complicated. If we have 3.5 moles of hydrogen, 3.5 moles of hydrogen, I'm going to erase these factors here. 3.5 moles of hydrogen, how much NH3 would we be able to make? And to do this, we're going to set up another conversion factor. We're going to multiply it by something, and it's going to be a fraction, because it's always a rate, it's always a fraction. What are we multiplying by? What's on top, what's on bottom? Well, whatever we're canceling has to be on the bottom, so H2 has to be on the bottom, and it has a 3 in our reaction, so 3H2. We're looking to make NH3, which means that we want NH3 to be left behind when we cancel out our fractions. So NH3 on top, and there is a 2 there, right? So the H2 is going to cancel the H2, and the NH3 is going to stick around. We're going to have some amount of moles of NH3. So that's going to be 3.5 times 2 divided by 3. That'll give us our mole. Well, really 3.5 moles times 2 divided by 3. Moles is like billion, if we remember. So 3.5 times 2 divided by 3. 2.33333333. So 2.3, I'm going to go 2.33. 2.33, right? 3.5 times 2 divided by 3. So you see here how the conversion factor method is great, right? It's hard to get lost when we use conversion factors because you have to keep in mind just how fractions cancel out, that the top is going to cancel the bottom. You're going to leave that behind. All right. And the last one here, we have a certain number of moles of NH3, 0.543 moles. Remember that a mole, like a billion, you can have 0.543 billion of something. You can have 0.543 moles of something. And we're going to try to convert it to moles of H2. We're going to create a conversion factor. NH3 is on top. We want to cancel it by putting NH3 on the bottom. And NH3 has the coefficient of 2 to NH3, so that's going to cancel out nicely. We want to make H2, and that's H2 up here. We want to leave H2. And it's got a 3 in front of it, so a 3. So in this case, we're multiplying by 3 and dividing by 2. And we get out the calculator. Do ourselves a little mole ratio. 0.543 times 3 divide by 2. I get 0.8145. 8145 moles of H2. And that's how you do a mole ratio problem. One thing, we're going to finish this off with one last piece, which is limiting reagents. We're going to talk about that briefly. So we're going to talk about limiting reagents quickly and how the mole ratio can help us figure it out. And a limiting reagent is something that limits how much product we can form. and other reactants are going to be in excess. So for example, if I was making a sandwich and I had 48 slices of cheese but only 16 pieces of bread, right? It doesn't matter how much cheese I only have 16 slices of bread. I can only make 8 sandwiches. I'll have a bunch of cheese left over, but I can't make a sandwich out of cheese. So that's the concept, we have something that can limit how much we can make. To figure out what is limiting, sometimes it's pretty obvious. So like if you dissolve this in a big beaker, there's obviously a ton of water and not a lot of magnesium oxide. So water is going to be in excess water, things like that. You'll see this a lot in reactions. They'll say something is done with excess acid or something is done with excess oxygen. Complete combustion has an excess of oxygen. The fuel is going to be the limiting reagent in complete combustion. To figure this stuff out, you're just going to figure out how many moles of each reactant and how much product each reactant can make. So here's a question. If we have this reaction, hydrogen and oxygen, and we want to make H2O, which one of these two is limiting reagent? Is it the hydrogen or the oxygen? Well, we have more hydrogen, but it takes twice as much hydrogen as oxygen to make the reaction go. So I'm going to go over to the whiteboard and we'll talk about this one. So the question here is which one is limiting? And here's our reaction and here's our numbers. We have 6 moles of hydrogen and 4 moles of oxygen. Which one is going to limit our reaction? Well, one way to do this is to work out how much water each one can make. Right, how much water can each one make? Well, to figure that out, we want to get water. We want to get how much water. So we need a conversion factor. H2 is going to be on the bottom, H2O on the top because we want to cancel our H2 and leave water alone. There is 2 H2s for 1 H2O, so we need 3 moles. We can make 3 moles, right? 6 times 1 divided by 2 is 3. This one we're going to make a conversion factor for the oxygen, and in this case the oxygen's on top. We want to cancel it with oxygen on the bottom. 1 oxygen in our reaction, 1. H2O, there's 1 of those. We want to make H2O, right? 1 H2O. So our 4 moles of oxygen can, obviously enough, make 4 moles of H2O. So with 6 moles of hydrogen, I can make 3 moles of H2O. With 4 moles of oxygen, I can make 4 moles of H2O. So this is the limit. All right, there's the limiting reagent. Now there's a second way to do this that is much faster, but conceptually a little bit harder to understand. And that is to just straight up divide the amount of moles by the coefficient that you have. So for example, here I had 6 moles of H2. I'm just going to divide it by 2 H2s, right? Divide it by the 2 H2s that we get from our formula, divide it by that. And that gives me, well, the H2 is going to cancel, and I get 3 moles. But 3 moles of what? It's just 3 moles. And it's 3 moles of the reaction. You can think of it as like a recipe, like, you make cookies and it says it makes a dozen cookies. Well, you can like double the recipe and make 24 cookies. Well, I can do this reaction. If I have 6 moles of H2, I can do the reaction 3 mole times, right? 3 mole repetitions of the reaction, like 3 billion repetitions of the reaction, because I have 6 billion of that ingredient. If I do it with oxygen, we take our O2, right? We have, in the question, we had 4 moles of it, 4 moles of O2. And we are going to divide it by the coefficient of O2, which is just 1, right? 1 O2 every time a reaction happens. And we can then run the reaction 4 mole times. So this one can run 3 moles of the reaction, this one can run 4 mole repetitions of the reaction. And you can kind of do it with, it's O2 per reaction. And this one could be H2 per reaction, kind of thing. All right, that's that. That's the whole lesson. Thanks for sticking around. And we're going to do a bunch of these practice problems in class like we normally do. Yeah, see you in class.